All right, so welcome to episode 27. I keep forgetting to change these until I'm recording. Episode 27 of Introduction to Quantum Field Theory, and we'll be talking about the Klein-Gordon equation Green's functions. Or actually, it's Green's function. So we'll talk about the Green's function for the Klein-Gordon equation. So let's get into this. To find the Klein-Gordon equation, Green's function, we would have to solve this inhomogeneous equation, the Laplacian plus m squared of the special solution of the field. We'd have to solve this when it's equal to the Dirac delta right here. So this is actually beyond us for now. So solving this is mathematically beyond our capabilities right now, beyond us, right? Cannot spell right now. Uh, cannot do this correctly right now. Cool. So we will assume we know it already. So we will assume we know the solution already, and we'll say that it's the following. The special field solution is the integral over the wave vector space, which is basically, it's just momentum space, but you're off by a factor of h bar. So you're over basically momentum space. Then there's a fraction, e to the minus I k mu of x mu minus y mu all over minus k mu plus m squared. And we will actually add, or we'll do this. So we're going to simplify it as the same way we had it last time, where I broke the exponential into two terms. Where we now have the the x variable and the y variable and their opposite they go in opposite phase direction. So this is minus I, this one's positive I. And if you recall, this right here, this will give the this doesn't give the Dirac delta, does it? No, it does. It does give the Dirac delta. I'm being silly. Yeah, look up here. This is the thing. It gives the Dirac delta. So this is the Dirac delta, then divided by some constant. We can check that this explicitly solves this equation. Technically, we know that it does already because this right here is the Dirac delta, and then this will be kind of the magnitude of this, as we'll see. So let's check that it solves this. So we will plug this in. So we'll say this implies that the Klein-Gordon equation, which is or times this is just equal to this times this quantity right here Okay, so we can we can actually, because these derivatives depend on space, and this is an integral over wave vector space, not space-time, we can move this integral out to the front. So that's what exactly I will do. And then we can into, move this in here, get rid of this. Then I'm going to take this right here and plus m squared times this quantity. And then there will be this factor right here of 1 over. Okay, so then the next step is to carry out this derivative. So this right here, if we recall correctly, I can get that to form a box or not. Form a box, please. There we go. So the partial derivative, or superscript mu, rather, it's the covariant or the contravariant gradient is partial over partial x mu here, like this. So this will give a minus I k superscript mu, and then the derivative of this will be 0. So moving to the next step in the equation, taking the derivative here, gets rid of this, and we end up with this still here, but we end up with a minus I k superscript mu, like so. And let's just move this all a little bit that way. And then taking the derivative one more time, what we can do is, because if we swap both indices at the same time, then it's exactly the same quantity. And this is going to take advantage of the fact that the covariant gradient is actually with respect to the contravariant position. So this will give a minus I times k subscript mu here. And these i's will cancel, or square root of -1. So we get this derivative goes away, and we get another minus I, and then we get k mu. Well, we can simplify this. The i's will just square and give -1. So we get negative k mu k mu. Well, now look at this equation. It has the exponentials here, and these are just constants. And these constants right here, so if we pull this out to the side, we just have minus k mu squared, minus k squared plus m squared. And here we have minus k squared plus m squared. So actually, the coefficients of of the denominator here and the numerator actually cancel. So we just end up with this term right here. So we end up with this, except this cancels with this, and all of this kind of just goes away. So we get this right here, which, as I said before, is just the definition of the Dirac delta. So this is exactly how This is exactly how it solves the inhomogeneous Klein-Gordon equation. So notice that here, this is very precise in space. So to be precise in space, you must. I've been writing my O's like A's lately, and it's bothering me. To be precise in space, you must sum over all k, which is exactly what's happening here. So this is basically the uncertainty principle, but it's really not a thing fundamental to quantum mechanics. It's just a statement of, in order to consider something highly localized at a single point, you have to consider all possible configurations of the field. So if you consider all possible configurations, then you can know for certain what something is at some point. And that's all that this is saying. So now let's talk about the physical interpretation a little bit. So if we take the inhomogeneous Klein-Gordon equation, the physical interpretation the physical interpretation of the Klein-Gordon equation is of a free field, because think about this right here. This basically is zero everywhere except for a single point. So it's essentially a free field, except there's one disturbance. So it's a free field with a single disturbance at x mu equals y mu. So single disturbance at x mu equals y mu. So you can imagine scaling the value at this position, and then summing, and then summing over all y mu to obtain the total disturbance. Or a better way to put this is interaction. So then a general solution that depends only on one position space is then the integral over all y, some interaction term, where the interaction term was defined in the last video, times this special function. So really the total interaction is the sum over all possible places where an interaction can take place, and then what the value of that interaction is. So the total interaction sum of all possible places of interaction, and then the scaling of that interaction, how strong it is. So let's take a final look at a simplified version of this F or this phi S. So in a one-dimensional case, you have that the special function is going to be a position, it's going to depend on position and then some other position, x prime. And then it's going to be a sum over all possible wave vectors. And this will look like minus I, k, and then position minus the other position. This would be minus k squared plus m squared. Then, via some complicated math that we don't know yet, this ends up being equal, like, so if you perform this integral, it ends up being equal to 1 over 4 pi r e to the minus m, where m is the mass, and then r, where r is the magnitude of the distance x minus x prime. So this right here, this is called the Yukawa Yukawa potential. Actually, can I remember how to spell this in Japanese? Yeah, so uh, okay, I don't remember what the last one. I get that symbol confused with the symbol for, or with the word for, or with the letter for a day. So, but anyway, this is the Yukawa potential, and we can visualize it by drawing a graph. So if this is your distance, and if this is the strength of the field, then near the center, it's going to be really high, but then as you go farther away, it goes to 0. So this is a Yukawa potential. And this makes sense that it tells you that if you're farther away from an interaction, you're not going to feel the effects of it as much. So the Yukawa potential basically encodes for how far things can interact.